Welcome to our session today, Accelerating Insights with the Health Analytics Platform. I'm Marianne Slight, a product manager on the healthcare team of Google Cloud, and with me is my colleague, Vivian Neely, who leads the healthcare customer engineering specialists. We're going to talk today about clinical data and the challenges facing health systems as they deal with a proliferation of EHR instances and ancillary clinical systems. So how do you get your data into the new standards FHIR or into the OMOP common data model? How do you align your different modalities of data, your different terminologies of data? How do you create and manage the pipelines to handle that data transformation? How do you abstract out structured data from the unstructured clinical note? And then how do you analyze this data in a coherent fashion without needing advanced SQL skills? These are the challenges that we're going to talk about within this presentation. So let's start off by talking about data harmonization, how you harmonize all of your different siloed data sources into something that's coherent and ready for analysis. And typically you might have several different EHR instances, each of which is configured differently from the next. Or perhaps you've acquired hospitals and they use a different EHR system than you do. As well as the EHR data sources, you also have clinical ancillary systems like lab systems or pharmacy systems. And all of this data harmonized into something coherent enables you to analyze more richly your clinical environment. But it's not just current data that's important, you also need to add on the historical data. And so what we typically see are historical data sources that come to Google Cloud in the form of CSV files or databases, with incremental or streaming data coming in through HR7 version 2 or using the new FHIR standard. And that's dealing with the data sources. What you harmonize to is over on the right-hand side, some kind of target schema. And that might be something like the FHIR schema, or it might be something like the OMOP observational common data model that is used for analyzing data for research purposes. But most commonly, it's some combination of a standard schema and then custom extensions in order to support any investments you've already made for applications that sit on top of it. And so supporting custom schemas is also part of our data harmonization suite. Now, in order to go from your data sources into your target schema, you typically need to have your data undergo 4 types of transformation. The first of these is field mappings, where perhaps you're taking patient_ID in this database over here. You've got MRN, or medical record number, as the name of the field over in this data source, and perhaps you've also got member ID in another data source, and you're trying to harmonize it into, say, the FHIR schema with the patient resource and the identifier attribute. That's field mappings. Terminology mappings looks at how you label the clinical concepts within your data. So perhaps you're capturing your medications using First Data Bank in this EHR, but over in Cerner, you're capturing them using the Multum medical terminology. And perhaps you want to harmonize those into RX norm. These are 3 different clinical terminologies that are used for medications. And you need to be able to harmonize the concepts into a coherent single clinical terminology for each of your different concept types. Units alignment is another step within data harmonization because different lab systems produce the lab test results with different units. Often that's just by a factor of 1,000, but sometimes it's a little more broader than that, as when a particular lab test, its standard unit of measure changes at a particular point in time. And in that case, the system needs to understand the point at which the units changed from one to another in order that you can end up with harmonized data in consistent units in your analytic target. And finally, abstracting out structured data from the unstructured clinical note. And I'll talk more about that in a moment. So we recently launched our mapping configuration language, which we call WHISTLE. And we've launched this to open source so that the entire community can benefit from this. What the WHISTLE mapping configuration language does is it enables you to convert from an input in JSON format into an output in JSON format using a mapping configuration that you've written using WHISTLE. And what's unique about WHISTLE is that it supports repeated and nested structures, which of course are so critical within support for HL7 version 2 and within support for the FHIR standard. It also supports calls for terminology maps, calls for unit harmonization, and for clinical entity extraction using natural language processing. And you can create your own user-defined functions as well. Now, here's an example of how you might convert an HL7 message that incorporates the name and address of a particular health system into FHIR. And the grey box at the bottom, that's an example of the WHISTLE mapping configuration that you would create to do that. When we launched our WHISTLE data transformation language within our open source GitHub repository, we also launched sample maps to get you started. We included sample maps for 2 different message types of HL7 version 2 mapped to FHIR, and we also included sample maps for mapping from FHIR to OMOP. And these are all available within our GitHub repo. So you've created this WHISTLE mapping configuration. Now how do you run it? We have 3 different ways that you can run a WHISTLE mapping configuration, create a pipeline, and convert your data. The first is using the Google Cloud Healthcare API. So if you're importing your data from cloud storage into the FHIR API, or if you're exporting your data from the FHIR API into BigQuery, or if you're moving your data from the HL7 version 2 store into the FHIR store on Google Cloud, in each of these cases, you can incorporate a WHISTLE mapping configuration to transform the data as you move it across. The second way is using Cloud Data Fusion, which is a Google tool that is a fully managed service for ETL pipelines. And what that allows you to do is have access to a library of different pre-configured sources and connectors and transformations, and a library of pre-configured outputs or sinks as well. And what's really unique about Cloud Data Fusion is that this is a fully managed environment that does it by drag and drop using a graphical UI. And that helps you to get away from managing all of your pipelines with code into focusing on the actual transformations that are getting done and moving you away towards insight and action. The third way is an open sourced cloud data flow pipeline that we launched earlier that converts this reference pipeline converts streaming HL7 version 2 messages into FHIR resources. And so that too is available on our GitHub repo. Now, I want to talk about clinical notes briefly in a bit more detail. This is an example of an ICU note. It's very dense. This is just a very small section of what's typically reams of paper, if you were to print it all out. It's reams of paper because a lot of it is copied from one note to another. It's copied forward. But the other issue with these kinds of notes is it's difficult to find the real wealth of information that's buried in this density of text. And it's dense because there's a lot of different types of abbreviation. It's also dense with a lot of different weirdities or oddities in punctuation, because some of this note is actually generated by the EHR. And then it's not just speaking English, it's also speaking Latin as well. And what's challenging about the clinical note is when you look at it, each of these different roles might see something different. So when a physician looks at that note and says, well, does this patient have sepsis? They will be looking at it from a different perspective than the medical coder, than the CDI nurse, than the clinical quality analyst. The physician is typically looking at it to say, could this patient possibly have sepsis? Because if so, he or she is going to do something different as a result. They're going to follow a different care pathway. whereas the medical coder is looking at the note to say, does this note justify a diagnosis of sepsis? Because if so, that will result in a different code on the medical claim. They undergo different training, and these different roles are looking at it, one from the perspective of discovery, the other from the perspective of compliance. So there are different models for these different use cases, and clearly one size does not fit all. And so what we are looking at in terms of clinical entity extraction are these 4 areas. The first is abstracting the actual clinical concepts themselves, the diagnoses, the medications, the procedures, the observations, and so on. The second is looking at the relations and the attributes about those key clinical entities. So, for example, with medications, what was the dose? What was the route? When was it ordered? Functional features talks about the semantic context of the clinical entities. So was that diagnosis actually positive for the patient, or was it documented as a rule-out diagnosis? Did this other diagnosis impact the patient, or instead did it pertain to the patient's parent, and actually it should be part of family and medical history? Terminology mappings, because when you abstract out this data, it needs to be coded into one of those clinical terminologies that the rest of the structured data described as. I said that one model doesn't fit all, and so we also enable tuning of these clinical entity extraction models using AutoML. And AutoML allows you to augment or enrich a model with a sample of your own data that you have labeled for your unique documentation practices, or perhaps you have unique abbreviations. Perhaps you've got specific use cases that you need to support, and AutoML allows you to tune that model for your specific circumstance. So you've harmonized your data using our data harmonization tools into something coherent. Now, how do you analyze it? Leveraging BigQuery enables us to provide scalable analytics. It's analytic database because it's structured as a columnar database, and it's scalable because it scales through petabytes horizontally. All of the data is encrypted both at rest and in motion by default, and the data is accessible using SQL. So all of those business intelligence tools over on the right-hand side can access the data within BigQuery using their native capabilities. We also have a number of public data sets available on BigQuery for you to integrate into your analysis as well. And we recently launched the OMOP Common Data Model as an open source GitHub repo on top of BigQuery, and further the Atlas cohort definition tool on top of Cloud Marketplace in Google Cloud. And what that allows you to do is to use the OMOP Common Data Model and analyze the data on BigQuery directly. So understanding the terminologies, the vocabularies, looking at database level statistics, understanding your patient profiles, and looking at your cohort definitions using the Atlas tool, all directly on top of BigQuery. This is an example of the Atlas Cohort Manager tool, looking at the prevalence of medications in this data set and understanding the different medications and their prevalence. I said we had a number of public data sets available. This is a subset of the healthcare data sets that are available on BigQuery. The first two are large synthetic data sets in 2 different forms to allow you to experiment with these different types of data. The first is FHIR, using the synthetic data from MITRE, and then the second is SynPuff, using synthetic data in the OMOP Common Data Model. But as well as those 2 synthetic data sets, we have a large number of curated current data sets. Most recently, we've added data sets in the fields of social determinants of health, and these are kept current every quarter and take social determinant data, such as income data, SNAP data, homelessness, down to, in many cases, the county level, so that you can mash this data with your own health system data in order to understand the impact of social determinants on your particular population. We also added the COVID-19 case data from the New York Times, and then there are a number of other data sets, healthcare data sets, that are available and kept current, and we're adding more all the time. Finally, how do you analyze data? You analyze data using dashboards often in order to generate action. So what are the decisions that you want to make on the basis of that analysis? Well, dashboards, and in particular our Looker offering, enables you to look at key performance indicators from your health system. In this example, I'm looking at readmission rates, mortality and average length of stay across my entire hospital system. Obviously, I can look at that over time. I can drill into specific facilities. Over on the right-hand side, you can see that I'm looking at some of the key diagnoses and procedures, those costly, chronic, often comorbid conditions, and looking at where I have potential to improve those key performance indicators. And I can drill into that in more detail. And if I drill into, for example, AMI, then I can see for my AMI patients, those on the right-hand side who are most at risk of bouncing back with a readmission. And that risk score has been generated using a machine learning model directly within BigQuery, using a BQML model that takes advantage of some of the public data sets that we looked at earlier, some of the social determinant data sets, but also takes into account things like the number of comorbidities and the discharge date relative to now, as well as the age of the patient. And so finally, these are some of the demonstration of the correlations between the risk score and some of the social determinant data. In these examples, household income data and SNAP enrollment data. So we've talked about the capabilities of the healthcare analytics platform. Let's talk about one specific use case, and that's a clinical data cloud for FHIR, because increasingly we're seeing FHIR in use in health systems as its central repository, real-time repository for clinical data because of its longitudinal patient record support. And so in this example here, you harmonize your data into FHIR using the tools that we've talked about for data harmonization. You make the data available in analytics on BigQuery. You store the data natively in the Healthcare FHIR store as part of the Healthcare API. All of this sits on top of the data protection suite, which encompass our support for HIPAA best practices. And we also enable access to that data through the FHIR application layer that includes Smart on FHIR and also Apogee. And now I'm going to hand it over to my colleague Vivian Neely, who's going to talk about the architecture.
Thank you, Marianne. So when we think through how data flows through this system, there are 5 conceptual steps it takes to get to a place where users can surface it to applications or perhaps to their analytics use cases. As Marianne discussed, there are a vast amount of data sources that can be ingested, from EHR data to patient-generated data, even with imaging data. All of these different source systems result in different products being utilized for data ingestion. Our healthcare API, for example, takes 3 different modalities: FHIR, DICOM, and HL7. While as something like our cloud storage or blob storage product can handle a wide variety of data that may be coming from data warehouses or patient or other data sources, truly. The data harmonization layer is really where the magic happens. All the aspects of harmonization are handled in this step, including utilizing the WHISTLE transformation language in order to get your data to a common data model it can persist in. While this architecture highlights utilizing Cloud Data Fusion for harmonization, as Marianne discussed, users can also leverage our Google Cloud Healthcare API or Cloud Data Flow as the infrastructure to do these transformations. Once it's in a persistent layer, whether that be in the healthcare API under FHIR or perhaps in BigQuery, we really move to the enrichment stage. And this is where users get to explore their data and drive insights from their data. So users can connect with the plethora of other Google Cloud products, such as our AI platforms or AI platform notebooks, which is really just a managed Jupyter notebook. We even allow for applications that are hosted on our marketplace for VM images to be able to use some of the other applications that are being publishing by other institutions within your data set. The second architecture that I go over is really more of a technical architecture of the flow of the data. As I discussed, the various different source systems result in various different ingestion processes. So while batch data or historical data might come in on cloud storage, real-time data comes in usually within HL7 v2 or perhaps device data. That's going to be handled on a transactional database and may land in the healthcare API store or one of our other application-based products such as our App Engine. The transformation and harmonization step here is happening with Cloud Data Fusion. And then there's various different ways that the data can be handled. Metadata can appear one way, and other data, such as your analytics data, your de-identified data, can be surfaced through BigQuery and utilized with products such as our private catalog. I'm now going to show you a demo of the solution we discussed.
So now we're going to be demonstrating that end-to-end architecture that we just talked through. From an input, in this case an HL7 message, to transformation, storing it in a Firestore, and exporting it to BigQuery. What's going to be sending our HL7 messages is a tool called Simulated Hospital. Google has open sourced this tool, and essentially what it does is it sends synthetic HL7 messages to whatever application you're looking to test. It allows you to choose how many pathways per hour. For this case, I'm going to turn it all the way up for the demo. This source code can be found at Google/SimHospital. We're going to hop to the pipeline. This pipeline has been built in Data Fusion. Data Fusion is great for users who are more familiar with UI-based pipeline building. It's running on top of Dataproc, or really our managed Hadoop product. You can see here we have plugins and inputs and outputs for each of the step of the pipeline. Our HL7 store pub sub, if we look into this, we can figure out which subscription we are listening to, what the naming is, and truly where it's coming from. We're currently at 200 HL7 messages. Hop to 201. So as we're going through the demo, you can see and fundamentally watch each of the messages go through the steps and how long it takes for them to get to the Firestore and be able to write. These mapping boxes are calling our WHISTLE code. What WHISTLE is we have open sourced a configuration language that allows for arbitrary JSON to arbitrary JSON. We have also open sourced reference mappings for HL7 to FHIR, and we are utilizing those reference mappings during this demonstration. So what that means is you can pull both this pipeline as well as our reference mappings to be able to automatically spin up or quickly spin up a HL7 to FHIR pipeline in your environment. We've stored those on a GCS bucket, you can see here. And over in the properties for the Firestore, it will tell you where the Firestore is located, the dataset name, and Firestore ID. We can also look at the documentation and the metrics to see how frequently data is writing to the Firestore in this pipeline. So if we hop over and we want to look a little bit more into this mapping WHISTLE configuration. First, though, I'm going to go into BigQuery. This is where the final data is being written. So from the Firestore, it is being exported and streamed into BigQuery. It is falling into this FHIR data set. You can see each of the resources creates a table within BigQuery. So just to test that we are indeed sending data, I'm going to run a count of the number of observations in my data set. We're currently at 18,912. So I'm going to hop over to our Jupyter Notebook demonstration and go back to this just to prove my honesty of the streaming real-time capabilities of the pipeline. So here in Jupyter Notebooks, we have also open sourced fundamentally a UI for users to be able to understand, evaluate, and reference against their WSTL code. It also does some FHIR validation that I'll walk through as well. For the input, the HL7, since WSTL is a arbitrary JSON to arbitrary JSON logic, the HL7 messages that are traditionally text-based messages go through our HL7 parser to then be transformed into a JSON object. So I'm going to be loading that JSON object from Google Cloud Storage into our notebook here. We can look at this. This is an ADT message. The MSH header is here. And this is how the parsing logic treats the message in each of the segments. So now we're going to actually go transform that message. This particular magic command lets users execute the scripts. You can display it in real time. You can then use it to go store as another variable. It will show you what the FHIR bundle looks like at the end of your WSTL code. So we're going to be processing the ADT. We've defined that in previous, in the open source code that I'll show in a minute. I'll go ahead and run this. So you can see it's creating a transactional bundle with several different entries. This particular one is requesting, so it's going to be, the request method is a put to the FHIR store, and it's putting an organization ID. Each of these functions that I'm calling are stored in various different areas of the open source code. So messages, for example, we can see here's the code that's defining how to transform your ADT message. We also have the segments WSTL. So this is the code that was defining that MSH header. All of this, again, is available open source on our Git repository. So we can go back here and now test out whether or not that FHIR resource we just created is actually going to be written and valid for the FHIR store. So we're going to transform another message, and then we're going to check its validation. So this is an invalid FHIR resource. I actually did that on purpose just to demonstrate the ability for us to, on the fly, make changes that then can be affecting of the validation. So hopefully when we try this again, we can see here it is indeed a valid source. So now it's going to be writing to the FHIR store. And everything that we do on this Jupyter Notebook actually changes the Google Cloud Storage and WSTL code you're utilizing. So this can be a very valuable tool for folks who are more familiar with the notebook-like interface. Again, all of this is open sourced at Google Cloud Platform's Git repository at healthcare-data harmonization. So now if we hop back into BigQuery, let's run this command again. Great, it went up. And so you can see the streaming results of this is in real time on how many observations it is actually writing into the BigQuery data set. Now for FHIR, for those who are familiar, it can be a pretty complicated data format and data standard to utilize. So a little bit more complicated of a query can be found here. Essentially what I'm going to be doing is pulling some patients from the patient resource. Since the patient or all resources are nested and have arrays in them, you have to use the safe offset command within BigQuery. It allows you to see a flat view of patient IDs, phones, birthdays, addresses things like this. Now, for those who don't want to write such a complicated query against BigQuery, or maybe are just not as familiar with SQL, we had a recent acquisition, Looker, the semantic layer within Looker actually can understand the FHIR data standard and write the queries for you. So it can take that complicated nests and arrays within, unnest it on the fly, and create beautiful visualizations for this complicated data model. Here we have an example of a patient that is utilizing Looker, and their data is stored in the FHIR data standard. So you can see they're from Massachusetts, 80 years old. This is an encounter timeline. The larger diamond is, the longer the encounter was. And you can kind of see their vitals over time. This can be effective patient management for doctors or clinicians to be able to understand what their patient looks like across the continuum of care. We then can also go over to more of an administrative view, which is allowing for us to visualize how many patients is going through a system, what's the average length of stay or readmission rate, as well as an overview of your population. For any of these particular statistics, we actually have the ability to drill into them. So I have the ability to drill into and see each of the patients that are making up that statistic. If I'm interested in this particular patient, I have the ability to follow up with him or see his overview, which is that very similar dashboard to the last one we were seeing for each of the individual patients. Looker can be a great tool to abstract that complicated data model into a layer that you are able to drive meaning from, gain insights from, as well as even do some machine learning modeling here.
Thank you so much for coming. For more information, check out our harmonization GitHub repo and contact your sales rep on how to get started.